So let's go ahead and look at some of these thermodynamics problems that were from the Project Lead the Way activity. To start that, I want to go ahead and go over what some of the variables are. I have big Q, which stands for my energy transferred, and we measure that in joules. M is the mass. C is the specific heat capacity of the material, and that is a constant. You look that up if you need to, if it's not given to you. That's something that you don't have to find. Um, it's a standard. It's a set number for each different material. Delta big T is our change in temperature. Over here we have P, which stands for our rate of energy transfer, and that's in watts. Once again, we have the Q. Delta little t is how much time, the change in time in seconds. Back over here to our P, that's the rate of energy transfer, and that's in watts. K is our thermal conductivity. A is the area. Delta big T back to temperature, change in temperature. L is the thickness of the material. And then this equation here to the right is the same as the last equation, just solved for a different variable. Let's take a look at the first problem. A 1 kilogram piece of aluminum metal at 90 degrees Celsius is placed in 4 liters or 4 kilograms of water at 25 degrees Celsius. We want to determine the final temperature. So looking at this and knowing what my variables are, having my variable sheet in front of me, I have 1 kilogram, which is going to be my mass. That's always measured in kilograms for us. We have 4 kilograms for the water. The aluminum was at 90 degrees Celsius when it was put in water that was 25 degrees Celsius, and I'm looking for my final temperature. So to list all of my known values, I know that the mass of the aluminum is 1 kilogram. The mass of the water is 4 kilograms. I know the temperature of the aluminum was 90. The temperature of the water is 25 degrees. And looking at these values, I need to know my TF, which in this case, it's the final temperature of both pieces, both the metal and the water. So knowing what I know, let's go back and look at our formulas. I've got a mass. I know I'm going to be messing with a change in temperature, but I only have one formula here that has a mass, which is what they gave me because they gave it to me in kilograms. So I know that I'm going to use only one equation. So Q equals M times C times delta big T. Looking back, so I need to know what C is for aluminum. And that's going to be 900. And then C for water is 4,184. So now that I have everything in here that I need except for my final temperature and my Q, so that's something else I would have to find, but let's think about Q for a moment here. Q is the amount of energy transferred. So if I take something that's hot and I put it in something that's cold, and you know that heat goes from hot to cold, I have energy coming out, or heat energy coming out of the aluminum going into the water. Well, we don't know that it's being lost anywhere else, so wouldn't the energy coming out of the metal be equal to that of what's the energy that's going into the water? If that's the case, then I have the Q of the aluminum is equal to Q of the water, so I can set the two equations equal to each other. So I have mass of aluminum times the C of the aluminum times the change in temperature is equal to the mass of the water times the specific heat of the water times change in temperature of the water. So the next part to think about now is how do I find my change in temperature? If we look back at our previous, we were given the starting temperature, 90 degrees for the aluminum and 25 degrees for the water. So we'll call that temperature initial. For the aluminum was 90. Temperature initial for the water is 25. But if I'm looking for the change in temperature, we need to think about, okay, well, how do I find a change in temperature? So I have a starting amount and I have a finishing amount. T final is going to be the same for both equations. So let's go ahead and think about this and write it out as we do that. So mass of the aluminum times the specific heat capacity of the aluminum times, we've got the aluminum initial, so temperature initial for the aluminum, minus the final temperature, because that's going to give me a number that is positive. My aluminum is going to go down in temperature, so that's going to give me a change in temperature in this area here. And then I do the mass of the water times the specific heat of the water times, we'll do the initial temperature, no, final temperature. We need to do final temperature because it's going to be getting warmer, so the final temperature is going to be higher than the initial temperature of the water. So now all I end up having to do is solve for my final temperature. So I need to solve for that just by doing some algebra. So let's go ahead and move to the next open area here and start plugging in our numbers. So the mass of the aluminum was 1 kilogram. The specific heat capacity of the aluminum was 900, and we knew the initial temperature was 90 minus our TF, and set that equal to the mass of the water was 4 kilograms times the specific heat capacity of the water times the final temperature minus our initial temperature. Let's go ahead and start doing some multiplication. So just following the order of operations, if I look in the parentheses, there's nothing I can do on inside of the parentheses. So then I look for exponents, none. Then I look for multiplications. Yes, I have one here and I have one here. So let's do those first. So then I get 900 times 90 minus TF equals 4 times 4184. Which is 16,736 times my final temperature minus my initial temperature. So now the next step, looking at this, I have yet another multiplication to do, but we need to distribute through the parentheses. So 900 times 90 is going to be 81,000 minus 900 TF, and then here I have 16,736 TF minus 418,400. So that's just a simple three-step algebra problem at this point. I need to get all of my variables on one side and all of my constants on the other. So to do that, I am now going to add 900 TF to both sides. Clean this up just a little bit. So doing that here cancels this out. I then have 81,000 And I'm adding 900, which makes this 17,636 times my final temperature minus 418,400. So ultimately I'm trying to get my TF by itself. So to do that now, I'm going to do the opposite of this subtraction. Which then gives me 499,400. And that is equal to my 17,636 TF. Only one step left. Divide both sides. And this is going to give me a number in degrees Celsius. So it's going to tell me that the final temperature of both the water and the aluminum comes out to 28.32 degrees Celsius. Couple of intuitive leaps in this problem, but not too terribly many. A lot of it is just stopping and thinking about what you're messing with and looking at what you've been given and what you've got to find. That allows you to go all the way back and look at your equations and figure out which one will work best for you, and then to take your time and plug in what you have and what you need, and then move through the general algebra.